Hello my friends, and welcome back to the YouCanDoTV channel. In this video, we will explore the production and installation of the world's largest hydraulic forging machine. In the next sections of the video, we will see the extremely interesting forging and machining operations at large factories. The manufacturing process of the 540 meganewtons pull-down press, the world's largest and most powerful hydraulic close-die forging press, was a remarkable endeavor in the field of heavy machinery production. This press, designed by the SMS Group, was specifically developed to meet the growing demands of the aerospace industry, where larger components with complex geometries require higher press forces for production. The manufacturing of the press involved multiple stages and required the collaboration of various foundries and machining facilities around the world. Large castings weighing between 100 and 310 metric tons were produced in foundries located in Korea and Great Britain. These castings, along with other forged parts, had to undergo precise machining processes to achieve the required levels of accuracy. After the large castings and forgings were produced, they were sent to specialized machining facilities located in Europe and Korea. Logistics played a crucial role in this global project. The large parts, including the castings and forgings, were shipped to different locations for further finishing and machining. Special machines in Europe and Korea were employed to ensure the high precision and quality of these components. One of the critical elements of the press was the 4 tie rods, which provided stability to the structure. These enormous tie rods, weighing more than 25 meters in length and with a diameter of around 1 meter, were forged on an open die forging press supplied by the SMS Group. The final assembly of the press took place at Weber Metals, a subsidiary of Otto Fuchs KG in Los Angeles. A deep pit, approximately 24 meters deep, was excavated to accommodate the press. The installation process involved careful lifting and transportation of the heavy components, such as the lower crosshead, which weighed a staggering 1,200 tons. Meticulous planning and execution were essential to ensure the precise positioning of each component in the confined space of the press pit. The assembly process of the 10,000-ton forging hydraulic press manufactured by Hydramec and purchased by Irizar Forge involved several steps and took approximately 3 months. The assembly process began with the installation of the press frame, which serves as the foundation of the machine. The frame provides the necessary stability and support to withstand the immense forces involved in the forging process. Careful attention was given to ensuring precise alignment during the installation to ensure the structural integrity of the press. After the frame was securely in place, 4 tie rods were installed. These tie rods are essential for reinforcing the structure and maintaining the stability of the press. They provide additional support and help distribute the forces exerted during operation. The tie rods were carefully positioned and secured, ensuring that they were properly nested within the press bed. The next step involved the installation of the press bed itself. The press bed is a critical component that supports the workpiece during the forging process. It is designed to withstand the immense pressure exerted by the hydraulic cylinders. The installation of the press bed required careful positioning and alignment to ensure that it would properly interact with the rest of the machine. During the installation process of the press, the use of mobile cranes and specialized lifting equipment was crucial for the safe and efficient handling of heavy components. Mobile cranes, equipped with powerful lifting capabilities, were employed to transport and position large and bulky parts such as the press frame and top frame. Their use allows for precise control and maneuverability, ensuring that each component is properly placed and aligned. Following the installation of the press bed, 3 hydraulic cylinders were installed into the bed. These cylinders are the primary driving force behind the press's operation, generating the immense force required for forging operations. Precise installation and connection of the hydraulic cylinders were crucial to ensure the press's proper functioning and efficiency during the forging process. Finally, the top frame of the machine was installed. This frame, along with the press bed and hydraulic cylinders, completes the overall structure of the forging hydraulic press. It provides additional support and stability to the machine, ensuring that it can withstand the high forces and vibrations generated during operation. The assembly process of the 10,000-ton forging hydraulic press required meticulous attention to detail, precise alignment, and the use of specialized equipment. The careful installation of the frame, tie rods, press bed, hydraulic cylinders, and top frame was crucial to ensure the press's reliability and performance. Now operational in the newly constructed forge shop, this hydraulic press stands ready to handle the demanding forging requirements of the offshore and onshore industry, producing high-quality hooks and safety-related forgings for global applications. Four-die forging devices are advanced mechanical systems used for the process of four-side radial forging. This technique is typically performed on hydraulic presses with impressive capacities of up to 125 meganewtons. The purpose of these devices is to efficiently shape and manipulate metal workpieces into desired forms with high precision and consistency. The operation of a four-die forging device involves a set of 4 dies positioned around the workpiece. Each die has a specific function in the forging process. The top die applies downward force to the workpiece, while the bottom die acts as a supporting surface. The 2 side dies exert lateral pressure, compressing the material horizontally. To begin the process, the workpiece is placed in the center of the 4 dies. The hydraulic press initiates the forging operation by exerting force on the top die, which pushes the workpiece downwards. As the material comes into contact with the side dies, they apply lateral pressure, causing the metal to flow and fill the cavities between the dies. The 4-die forging device operates in a cyclical manner. As the hydraulic press retracts the top die, the side dies release their pressure, allowing the workpiece to be repositioned for the next forging cycle. This cyclic process continues until the desired shape and dimensions are achieved. These devices are meticulously engineered to ensure precise control over the forging process. They incorporate advanced features such as adjustable die gaps, temperature control systems, and automated controls for accurate and repeatable results. The sophisticated design and construction of these devices enable manufacturers to produce complex metal components with excellent structural integrity and dimensional accuracy. Forging a pipe using a 4-die block and 2 forging manipulators involves a systematic process. The pipe billet is placed onto the forging manipulators, which are positioned in the 4-die block within a forging press. The press applies force, causing the top die to compress the billet while the side dies shape it into a pipe form. The manipulators rotate the billet for even forging. The temperature and speed of the process are controlled for optimal results. This forging cycle is repeated for different sections of the billet until the entire length is forged. The finished pipe is then inspected for quality and may undergo additional treatments if required. Seco Tools offers a solution for heavy machining with their SCMT38 tool. This tool is specifically designed for the cost-effective machining of large and heavy workpieces. In this case, the 25 metric ton rotor shaft was smoothly machined using the SCMT38. The tool features a screw clamping system and a positive insert, which ensures a secure and stable cutting process. One of the key features of the SCMT38 is its extremely wear-resistant duratomic coating, known as TP0500. This coating enhances the tool's performance during long machining operations where a significant amount of heat is generated. In this case, the insert SCMT25 is used with a powerful Poremba machine, measuring 12 meters in length and equipped with a 195 kilowatts motor. This insert is ideal for heavy machining applications, such as finishing a 20.8-ton rotor shaft made of special high-grade steel. Its robust design and cutting-edge technology enable efficient and precise machining of large workpieces. The insert ensures high performance and longevity, making it a reliable choice for heavy machining operations. This is the Geminis GHT 11G4 lathe. It is a powerful CNC machine equipped with the Fagor 8055 control system. It boasts a generous 5,000 millimeters distance between centers, allowing for machining long workpieces. The bed's impressive 2,500 millimeters diameter provides ample space for handling large-scale projects with precision and efficiency. Gemini's horizontal multi-process lathes are advanced machining tools designed to provide precise and efficient manufacturing solutions. These lathes offer a wide range of capabilities, enabling users to perform multiple operations on a single machine, thereby optimizing productivity and reducing setup time. At the heart of the Gemini horizontal multi-process lathes is a robust and highly rigid bed that provides excellent stability during machining operations. This stability ensures high precision and repeatability, allowing for the production of intricate and accurate parts. The lathes are equipped with multiple spindles and turrets, which can be independently controlled and synchronized, enabling simultaneous machining operations. One key feature of these lathes is their ability to perform turning, milling, drilling, and tapping operations in a single setup. This eliminates the need for multiple machines or tool changes, streamlining the production process. The spindles and turrets can be fitted with various cutting tools, allowing for a wide range of operations to be performed on different surfaces of the workpiece. Gemini's horizontal multi-process lathes utilize advanced CNC, computer numerical control systems, which enable precise control of the machining process. The CNC system allows operators to program and automate the machining operations, ensuring consistent and accurate results. Additionally, the lathes are equipped with sensors and feedback mechanisms that continuously monitor and adjust the cutting parameters, optimizing performance and enhancing tool life. The lathes also feature a user-friendly interface, which simplifies operation and programming. Operators can input the desired machining parameters and tool paths through the control panel or computer interface, and the machine takes care of the rest. The lathes can also be integrated into a larger manufacturing system, allowing for seamless production flow and efficient utilization of resources. The Gemini moving column milling and boring machine, commonly known as GMP, is an advanced machining tool designed for precise and efficient milling and boring operations. This machine features a moving column design, which offers enhanced flexibility and productivity. The key component of the GMP is its movable column that houses the milling and boring spindle. This design allows the workpiece to remain stationary while the column moves along the X, Y, and Z axes, providing greater accessibility and maneuverability. The moving column design also enables the machining of large and complex parts with ease. The milling and boring spindle of the GMP is equipped with a powerful motor and a variety of cutting tools. These tools can be automatically changed using a tool changer, allowing for seamless transitions between different machining operations without the need for manual intervention. The machine is controlled by a sophisticated CNC, computer numerical control system, which ensures precise control over the cutting parameters and tool movements. The CNC system of the GMP can be programmed with specific tool paths and machining parameters. Operators can input these instructions through the control interface, specifying the desired cuts, speeds, feeds, and other parameters. The CNC system executes the programmed instructions, guiding the machine to perform the precise milling and boring operations. The GMP is designed to handle heavy-duty machining tasks, thanks to its sturdy construction and high rigidity. This design minimizes vibrations and enhances stability during cutting, resulting in improved accuracy and surface finish. The machine is widely used in industries such as aerospace, automotive, and mold making, where precision and efficiency are critical. The HX500i Heavy-Duty Horizontal Machining Center, part of the Kitamura My Center series, is designed for high-torque machining applications. It features a robust 8,000 revolutions per minute 4-step geared, dual-contact spindle, optional, that provides enhanced cutting power. The machine utilizes an original shockless drive mechanism, which effectively minimizes vibrations resulting from milling cuts. Despite its powerful capabilities, the HX500i is designed to maximize space efficiency. It occupies a compact footprint while still accommodating a standard 35 HP AC motor. This motor enables the machine to handle workpieces with a maximum size of 31.5 in diameter and 42.9 in height. The HX500i is built to deliver exceptional performance in heavy-duty machining tasks. Its high torque capabilities, coupled with the advanced spindle design and vibration reduction mechanism, make it suitable for tackling demanding milling operations. Whether it's large workpieces or intricate components, the HX500i Heavy-Duty Horizontal Machining Center offers reliability, precision, and efficiency in a compact package. ZVU Kavarna is a well-known company specializing in the production of forgings and machining components. It is a Czech manufacturing company with a rich history dating back to 1871. It has a strong reputation for delivering high-quality products and solutions to various industries, including automotive, aerospace, energy, and more. They offer a wide range of services, including forging, machining, heat treatment, surface treatment, and assembly. The company's forgings are known for their precision, strength, and durability. They utilize advanced forging techniques and modern equipment to shape metals into complex and precise forms. With their expertise in material selection, heating, die preparation, and heat treatment, they can produce forgings with excellent mechanical properties. In addition to forging, the company also specializes in machining operations. Their machining capabilities involve the use of CNC machines, lathes, milling machines, and grinding machines to remove excess material from forgings or raw stock. They employ skilled engineers and technicians who ensure precise dimensions, tight tolerances, and high surface finishes in their machined components. ZVU Kavarna places a strong emphasis on quality control throughout their manufacturing processes. They have established stringent quality assurance procedures and utilize advanced measurement tools and equipment to verify the conformity of their products. By adhering to strict quality standards, they ensures that their customers receive components of the highest quality. The Hedelius Tiltenta 11 is a cutting-edge machining center that has gained significant attention in the industrial manufacturing sector. Developed by Hedelius Maschinen und Fabrik, a renowned German company known for its high-quality CNC machines, the Tiltenta 11 represents a significant advancement in precision engineering and versatility. At the heart of the Tiltenta 11 is its innovative tilting spindle head, which sets it apart from conventional machining centers. The tilting capability enables the machine to perform complex multi-axis operations with exceptional precision. This flexibility allows manufacturers to create intricate and sophisticated parts with ease. One of the key features of the Tiltenta 11 is its robust construction. The machine is built to withstand heavy-duty machining operations, ensuring stability and accuracy even during demanding tasks. The solid machine bed and high-quality components contribute to its overall rigidity, minimizing vibrations and enhancing the machining precision. Equipped with advanced CNC control systems, the Tiltenta 11 offers exceptional automation and optimization capabilities. The intuitive user interface allows operators to program and control the machine with ease, reducing setup times and maximizing productivity. The machine also supports a wide range of tooling options, providing manufacturers with the flexibility to select the most suitable tools for their specific machining needs. Another notable feature of the Tiltenta 11 is its high-speed machining capabilities. With a powerful spindle motor and high acceleration rates, the machine can rapidly remove material, reducing cycle times and boosting productivity. Whether it's milling, drilling, or tapping, the Tiltenta 11 excels in delivering swift and precise results. Furthermore, the Tiltenta 11 incorporates advanced coolant systems and chip management solutions to ensure efficient heat dissipation and chip removal. This feature helps maintain optimal working conditions and prolongs the lifespan of cutting tools, reducing production costs and downtime. Drive engineering plays a crucial role in the steelmaking industry, particularly in steel plants and rolling mills. The drive technology employed must meet the highest demands to ensure sturdy and reliable performance. This is essential to achieve top-quality products and maintain high plant availability for decades. SMS SEMA, a company specializing in drive systems and components, has been at the forefront of developing, designing, and manufacturing drive solutions for steelmaking plants and rolling mills. Their product range includes all drive systems for hot and cold rolling mills, as well as steelmaking plants. They supply main drive gears, mill pinion gears, twin drive gear units, and gear units for various applications such as shears, edgars, sizing presses, coilers, and more. Their spindles, including flex gear type spindles and slipper type spindles, are designed to meet the highest torque requirements for converters like BOF, basic oxygen furnace converters. Additionally, they provide tilting drives for specific applications. The fabrication of gear components takes place in SMS SEMA's advanced workshops. Modern machinery and equipment are utilized to handle the manufacturing process. In the welding shop, fully mechanized submerged arc welding is employed to create strong joints on the gear wheels. Welding is followed by a anneal process for stress relief to ensure the gears are structurally sound. After welding and stress relief, the gear wheels move to the machining and milling stage. State-of-the-art machines are used to mill the tooling with precision. Qualified personnel supervise this process to ensure accuracy and quality. To enhance the hardness and durability of the gears, case hardening is employed. The gear wheels undergo a case hardening process, which involves heating them to a specific temperature and then quenching them rapidly. This results in a hardened outer layer, providing excellent wear resistance. The next step is grinding the tooth flanks of the gears. This is done on a profile grinder to achieve the desired tooth geometry and surface finish. Grinding ensures smooth and precise operation of the gears. In addition to the gears, SMS SEMA also produces gear housings in-house. This ensures compatibility and seamless integration of the gear units. The gear housing production process is carried out using advanced manufacturing techniques. The gear components are pre-assembled, and the gear contact pattern is adjusted using eccentric sleeves. This allows for precise adjustment of the gear contact pattern and clearance, enabling optimal gear performance. The finished gears undergo high-precision tests on a separate gear measuring machine. This step verifies the dimensional accuracy and ensures that the gears meet the required specifications. Gear contact patterns and clearances are precisely adjusted using computer-aided programs. At Aleris Aluminum in Koblenz, Germany, SMS SEMA replaced the entire drivetrain in just a few days. The installation of the twin-drive gearbox was one of the most spectacular revamps in recent years. Without interrupting operations, SMS SEMA mounted the new drive and motors on a foundation block, which was then moved to the position of the old drive unit after completing all function tests successfully. This demonstrates the company's reliability and ability to execute complex projects. Throughout the manufacturing process, SMS SEMA maintains a high standard of quality control. Highly qualified and experienced employees work in production with regular advanced training to enhance their skills. Comprehensive service plans are also offered to maintain the performance of the drives, including inspection services and monitoring systems for the gear units. At Schoen AG, the manufacturing process for coiler shafts involves several steps to ensure the production of high-quality, ready-to-install machine shafts. Let's delve into each of these steps. Open die forging. The manufacturing process begins with open die forging. This process involves shaping the raw material, typically a high-strength alloy steel, into the desired coiler shaft shape using heavy machinery and high-pressure compressive forces. Open die forging ensures the creation of a sturdy and durable shaft with the required mechanical properties. Saws. After the forging process, the coiler shaft undergoes sawing to remove any excess material and to achieve the desired length and dimensions. This step helps in refining the overall shape of the shaft. Quenching and tempering. Quenching. After the coiler shafts have undergone the necessary machining operations, They are heated to a specific temperature and then rapidly cooled in a quenching medium, such as oil or water. This rapid cooling process helps to harden the material and increase its strength and wear resistance. Tempering. Following quenching, the coiler shafts are tempered. Tempering involves reheating the hardened shafts to a lower temperature and holding them at that temperature for a specified period. This controlled heating and cooling process helps to relieve internal stresses, improve toughness, and achieve the desired balance between hardness and ductility in the shafts. Material testing. Material testing is a critical aspect of the manufacturing process for coiler shafts at Schoen AG. These tests are conducted to ensure that the materials used in the shafts meet the required specifications and exhibit the necessary mechanical properties. Pre-turn. In the pre-turn stage, the coiler shaft is subjected to initial turning operations. This step involves removing any remaining excess material and preparing the shaft for subsequent machining processes. Rough and finish milling. The coiler shaft undergoes rough and finish milling operations to achieve the desired surface finish, dimensional accuracy, and geometrical features. This step helps in refining the shape and size of the shaft, ensuring smooth operation during coiling and uncoiling of sheet metal. Finish turning and grinding. In the finish turning and grinding stage, the coiler shaft receives final precision machining. This step involves refining the dimensions, surface finish, and tolerances to meet the exact specifications required for installation. Grinding operations help achieve precise roundness and surface quality. Drilling. Drilling is performed to create any required holes or bores in the coiler shaft, allowing for additional components or attachments to be installed if necessary. This step ensures the shaft is ready to be integrated into the coiling and uncoiling system. Non-destructive testing. To guarantee the integrity and reliability of the coiler shaft, non-destructive testing techniques are employed. Ultrasonic US testing and magnetic particle (MP) testing are commonly utilized methods to detect any potential defects, cracks, or irregularities that may affect the performance of the shaft. Packing. Once the coiler shaft has undergone all necessary machining and testing processes, it is carefully packed to ensure its protection during transportation and storage. The Decoiler straightener feeder system, manufactured by Coiltech, is a cutting-edge solution designed to streamline press feeding operations in various industrial applications. This compact system combines three essential functions into a single integrated unit, offering enhanced efficiency and productivity. The Decoiler straightener feeder system is a sophisticated piece of machinery that combines three essential functions: decoiling, straightening, and feeding. Let's explore how this system works to streamline press feeding operations. Decoiling. The system begins by unwinding the metal coil, which is typically stored on a reel. The coil is placed on the decoiler mandrel, and a motorized drive system smoothly unwinds the coil, releasing the material. The unwinding process is controlled to maintain tension and prevent material slack or snags, ensuring a steady supply. Straightening. Once the material is unwound, it may have coil memory or deformations. To rectify this, the system employs a straightener mechanism. The material passes through a series of straightening rollers that gradually remove any curvatures or irregularities, resulting in a perfectly flat and smooth strip of metal. The straightening process is crucial to ensure accurate and consistent feeding. Feeding. After the material has been straightened, it is ready to be fed into the press for further processing. The feeder mechanism takes control, precisely advancing the material at the desired feed speed. The feeder may utilize servo-driven rolls or pneumatic grippers to grip the material securely and move it forward with accuracy. The feed length and speed can be programmed and adjusted to meet specific requirements. The spiral manufacturing process starts with milling the edges of the steel plate to ensure smooth and precise edges that will facilitate a proper weld joint. Welding. The milled steel plate is then formed into a cylindrical shape and welded along the spiral seam. This is usually achieved by using automated submerged arc welding SAW techniques. The weld joint is continuously moved along the length of the pipe, creating a spiral weld. Quality inspection. After welding, the pipes undergo various quality inspections to ensure they meet industry standards and customer requirements. These inspections include visual examination, dimensional checks, and surface defect inspections. Hydrostatic test. The pipes are subjected to a hydrostatic test, which involves filling them with water or another suitable fluid under high pressure to check for any leakage or structural weaknesses. Radiographic inspection. In this step, the pipes are examined using radiographic testing, commonly X-rays or gamma rays, to detect any internal defects or welding inconsistencies. This inspection method provides a detailed view of the internal weld quality and identifies any potential issues that may compromise the pipe's performance. The Gorelacher Combi T. Spiro is a highly efficient machine designed to produce standing lockseam elbows and reducers. It utilizes two separate workstations, a flanging station and a seam closing station, providing high flexibility and eliminating the need for time-consuming conversions. This allows the machine to be ready for operation at all times. The first workstation, the flanging station, is responsible for creating the standing lockseam. This process involves shaping the sheet metal into a specific profile, typically a 90-degree elbow or a reducer. The sheet metal is fed into the machine, and specialized tools and rollers are used to form the standing lockseam shape. This standing lockseam design reduces the need for extensive welding, as it requires only one longitudinal seam. It also enhances the rigidity and strength of the final product. Once the flanging process is complete, the sheet metal moves to the seam closing station. Here, the machine seals the lockseam to ensure a tight and secure connection. Various mechanisms, such as rollers or clamps, are employed to close and lock the seam, creating a durable and leak-proof joint. The Gorelacher Combi T. Spiro is manufactured by Spiro International SA, a renowned industry leader in the development of machines for round ducting and fittings in sheet metal. Spiro is also a trusted supplier of fittings and system solutions for the ventilation and air conditioning sector. With their expertise and innovative technology, the Gorelacher Combi T. Spiro offers high production capabilities, precision, and reliability for the production of standing lockseam elbows and reducers in the ventilation and air conditioning industry. Manufacturing process of Laba-Laba Grating. The Laba-Laba Grating. produced by PT Multicolor Indonesia, is a versatile product widely used in various industries. This article provides an in-depth understanding of the manufacturing process of Laba-Laba Grating, focusing on the steps involved in small-size steel plate preparation, wire rod processing, press welding, and finishing operations. Small-size steel plate preparation. The manufacturing process of Laba-Laba Grating begins with the preparation of small-size steel plates. Wire rod processing. Simultaneously with the steel plate preparation, wire rods are processed to the required size for Laba-Laba grating production. The wire rod, typically made of low-carbon steel, is fed into a twisting machine. The machine twists the wire rod, increasing its strength and stability. After the twisting process, the wire rod is cut into pieces according to the desired dimensions. These wire rod pieces will be used to form the mesh panels of the grating. The press applies pressure to the steel plates, creating a serrated pattern on the surface. This process enhances the grating's slip resistance and provides a secure footing for users. After passing through the serrated press, the steel plates are cut into long pieces to facilitate further processing. Press welding process. The core manufacturing technique employed in Laba-Laba grating production is press welding. This process involves the use of a press welding machine that allows for the perpendicular insertion of steel wire rods into the steel plate, creating a robust and secure bond. Machine setup. Before starting the press welding process, the press welding machine is set up according to the desired grating specifications. This involves adjusting the machine's settings, such as wire spacing, wire diameter, and pressure, to meet the required design parameters. Steel wire insertion. In this step, the steel wire rods are manually or automatically fed into the press welding machine. The machine's mechanism presses the wire rods firmly into the pre-cut steel plate, forming a grid-like pattern. The direction of installing the steel wire rods determines the width of the grating, while the direction of installing the steel plate determines its length. Welding. Once the steel wire rods are correctly positioned in the steel plate, the press welding machine applies pressure and heat to create a strong metallurgical bond between the wires and the plate. The combination of pressure and heat ensures proper fusion and adherence, resulting in a sturdy and durable grating structure. Cutting and border formation. Once the mesh panels are formed, they are cut into smaller pieces based on the required dimensions of the grating. These smaller mesh panels will serve as individual sections of the final product. To reinforce and provide a finished look, the welders proceed to weld steel plates around the edges of the mesh panel. The steel plate acts as a border, covering the cuts made during the mesh panel formation process. This border also enhances the structural integrity of the grating. Finishing operations. To ensure the Laba-Laba grating's quality, appearance, and functionality, several finishing operations are carried out. Grinding. After the welding process, the welded sections of the grating are ground to ensure smoothness and remove any sharp edges or burrs. This grinding process improves the safety and comfort of users, preventing potential injuries or discomfort. Surface treatments. Depending on the desired characteristics and applications, additional surface treatments may be applied to the Laba-Laba grating. Surface treatments, such as galvanization or powder coating, can be implemented to enhance corrosion resistance, improve aesthetics, and provide long-lasting durability. Quality control. Throughout the manufacturing process, PT Multicolor Indonesia implements rigorous quality control measures. Skilled technicians conduct visual inspections, dimensional checks, and mechanical tests to ensure that each Laba-Laba grating meets the required standards and specifications. Non-conforming products are identified, rectified, or rejected to maintain consistent quality. GWF Mangale is a well-known manufacturer of high-quality large presses. One of their notable achievements was the production of an extraordinary 16-meter-long press brake as a standalone machine. The manufacturing process involved welding together multiple parts to create the sizable components of the press brake. GWF Mangale emphasizes the quality of the welds, ensuring they surpass the quality of the base material. This commitment to excellence guarantees top-notch results and showcases the renowned German expertise. To ensure the highest standards, all welds undergo thorough ultrasonic testing. Independent experts perform this examination, certifying the quality of the welds at regular intervals. Skilled workers detach the remaining brackets from the side frames using welding torches, while precise milling is carried out on one of the cylinders. Notably, this cylinder is the largest of its kind, currently employed in a press within Europe. It boasts a piston with a diameter of 60 centimeters, featuring a specially treated surface for enhanced performance. The press table is inverted to enable the milling of a 16-meter long T-slot. Threads for fastening are cut into one of the side frames, meticulously executed to ensure accuracy. The components are machined only after the welding process to achieve the highest level of precision. The rotary process is utilized to finely mill the support of the press table. Additionally, a 520 mm thick plate is drilled on one of the side frames, serving as a secure anchor for the foundation. The transportation and handling of the heavy components during the manufacturing process are made possible with various positioning devices. Careful attention is given to packaging, transportation, and delivery to ensure that the press brake reaches its destination safely and intact. Precise positioning of the left side frame is crucial to achieve the required accuracy for precise bending operations. Special attachments are utilized for the upper beam, and the back gauge is meticulously installed. The press table is supported by two mounts, allowing it to swing freely. GWF Mangale's long-standing employees, with their years of experience and expertise, consistently find optimal solutions to complex problems. The sheer scale of the press is awe-inspiring, measuring an impressive 16 meters in length and weighing approximately 850 tons. It spans the width of a basketball court and is almost twice as heavy as an Airbus A380. During many years, stainless steel and steel sheet parts have been expertly formed using this press brake, with a press force of 40,000 kilonewtons at Klostermann in Kastrup, Roxel. Special attachments are utilized for the upper beam, and the back gauge is meticulously installed. The press table is supported by two mounts, allowing it to swing freely. GWF Mangale's long-standing employees, with their years of experience and expertise, consistently find optimal solutions to complex problems. The sheer scale of the press is awe-inspiring, measuring an impressive 16 meters in length and weighing approximately 850 tons. It spans the width of a basketball court and is almost twice as heavy as an Airbus A380. During many years, stainless steel and steel sheet parts have been expertly formed using this press brake, with a press force of 40,000 kilonewtons at Klostermann in Kastrup, Roxel. The assembly process of the 6,000-ton press brake by Bakel machinery is a complex and meticulous procedure that requires the use of heavy machinery and skilled technicians. This press brake is renowned as the largest of its kind in the world, boasting impressive dimensions of 6,800 millimeters in length and a powerful 6,000-ton capacity. These are side frames, which are the main components of the press brake. These frames are meticulously crafted to ensure durability and precision. Once completed, they are carefully lifted and loaded onto trucks for transportation to the installation site. Upon arrival at the installation site, hydraulic gantry systems come into play. These hydraulic systems provide the necessary lifting power to handle the massive weight of the side frames. With the aid of these systems, the side frames are lifted off the trucks and positioned in the designated area. Mobile cranes are also utilized during the assembly process. These cranes are equipped with the necessary strength and mobility to handle the installation of such large and heavy components. The mobile cranes work in tandem with the hydraulic gantry systems to ensure a smooth and safe installation process. Throughout the assembly process, skilled technicians closely monitor and supervise the operations. Their expertise is crucial in ensuring that each component is accurately positioned and securely fastened. The technicians make use of specialized tools and equipment to handle the intricate details of the assembly. Once the side frames are successfully installed, the remaining components of the press brake, such as the hydraulic cylinders, bending tools, and control systems, are meticulously integrated. Each component is carefully aligned and connected according to precise specifications. After the assembly is complete, rigorous testing and quality control procedures are conducted to ensure the press brake functions flawlessly and meets the highest industry standards. These tests include verifying the accuracy of the bending angles, testing the hydraulic systems, and inspecting the overall performance of the press brake. The assembly process of the 6,000-ton press brake by Bakel machinery is a remarkable feat of engineering and precision. It showcases the expertise and dedication of the technicians involved in bringing this monumental machine to life. With its impressive capabilities, this press brake stands as a testament to Bakel's commitment to innovation and pushing the boundaries of manufacturing technology. At Klostermann, the presses are the backbone of their steel processing operations, providing the power and versatility required to shape and transform various materials. These state-of-the art presses are meticulously engineered to handle a wide range of projects, showcasing the company's commitment to precision and efficiency. Klostermann's press machinery is renowned for its impressive capabilities and advanced features. The company boasts a diverse fleet of presses, including the largest press brake in Europe, aptly named the Giant. With a remarkable force of 4,000 tons, this colossal machine is capable of exerting immense pressure, enabling the bending and forming of materials with substantial thickness and strength. The press brakes at Klostermann are specifically designed to accommodate different material types and thicknesses, ensuring optimal performance across various applications, from construction steel to light metals, stainless steel, and high-strength steel. These presses can handle a wide array of materials with precision and reliability. Operating the presses at Klostermann involves a systematic and meticulous approach. The material to be processed is carefully positioned on the press bed, ensuring proper alignment and stability. Once in position, the hydraulic system is engaged, which generates the force needed to shape the material. The upper and lower dies, strategically positioned on the press brake, apply controlled pressure, resulting in precise bending and forming according to the desired specifications. To achieve consistent and accurate results, Klostermann's presses are equipped with advanced control systems. These systems allow operators to finely adjust the press force, bending angles, and other critical parameters. Skilled operators closely monitor the entire process to ensure optimal performance and maintain the high-quality standards that Klostermann is known for. The presses at Klostermann are vital for the cold forming of components. With the ability to handle materials up to 20,000 millimeters in length and 200 millimeters in thickness, these presses excel in handling large-scale projects. The Trumpf TrueBend 5000 press brake is an advanced and innovative piece of machinery that revolutionizes the sheet metal bending process. This cutting-edge technology is highly regarded for its exceptional productivity, precision, and unmatched production flexibility. Its efficiency and versatility make it a top choice for operators in various industries, including sterling fabrication. One of the remarkable features of the Trumpf TrueBend 5000 press brake is its ability to bend 3 different parts with 3 different tool setups in under 5 minutes. This impressive capability significantly enhances the overall productivity of the machine, allowing operators to accomplish more tasks in a shorter amount of time. By eliminating the need for manual tool changes and reducing setup times, the TrueBend 5000 streamlines the production process and boosts efficiency. The precision offered by the TrueBend 5000 is second to none. With advanced sensors and intelligent control systems, it ensures accurate and consistent bending results. The machine's high-speed and high-precision bending capabilities guarantee that each part is formed exactly as required, meeting the most stringent quality standards. This level of precision not only enhances the overall product quality but also minimizes waste, as errors and rework are significantly reduced. Furthermore, the TrueBend 5000 press brake offers unparalleled production flexibility. It can accommodate a wide range of materials, thicknesses, and part geometries, making it suitable for diverse applications. The machine's user-friendly interface and intuitive programming features enable operators to quickly and easily switch between different bending tasks. This flexibility allows manufacturers like Sterling Fabrication to adapt to changing customer demands and rapidly produce a variety of parts with minimal downtime. The Chuangheng hydraulic guillotine shear is a cutting-edge machine designed to deliver high accuracy and superior cut quality across various materials. This shear operates on the principles of hydraulic and mechanical systems, offering reliability and precision in the cutting process. The machine features a sturdy and stress-free steel welded structure, ensuring stability and durability during operation. It is equipped with 3 guide trolleys that facilitate precise movement and fine shearing results. These guide trolleys help maintain the material in a secure position, preventing any slippage or misalignment during the cutting process. The blade holder is hydraulically driven and retracted by a cylinder accumulator. This hydraulic system ensures controlled and smooth movement of the blade, enabling efficient and accurate cutting. The Chuangheng shear also allows for adjustable rake angle, minimizing the deformation of the sheared plate and optimizing the cutting process for different materials. The back gauge travel of the machine can be manually adjusted using a knob, and it is digitally displayed for precise positioning. Additionally, the shear is equipped with a swing-away back gauge function, enabling the cutting of longer sheets with ease. One notable feature of the Chuangheng hydraulic guillotine shear is the indicator-based adjustment of blade clearance. This feature allows for easy, convenient, and swift adjustment of the blades, ensuring optimal cutting performance. The shear comes with 4 cutting edges blades, providing extended usage and reducing the need for frequent replacements. The stroke of the blade holder can be adjusted, offering flexibility and adaptability to different cutting requirements. The Chuangheng shear is available with either an NC controller as a standard configuration or a CNC controller as an optional upgrade. The CNC controller provides advanced automation and precise control, optimizing the manufacturing process and improving cutting efficiency. The Neelands SBP shipbuilding press is a specialized press designed to efficiently produce bulbous panels in shipbuilding. This advanced press combines 3 essential applications: bending, spot stretching, and rolling, making it ideal for shaping complex panels, including bulbous panels. Tooling setup. The SBP press is equipped with specific tooling to shape the bulbous panel. In this case, the process involves utilizing a combination of center stretching, rolling, and shorter bending tools. The tooling is set up on the press, ensuring proper alignment and secure attachment. Center stretching. To create the basic shape of the bulbous panel, the center lines of the metal sheet are given a stretch. This center stretching process involves applying controlled force to elongate the lines in the center of the bulbous bow. This initial stretching helps to establish the foundation for the desired shape of the panel. Rolling of center lines. After the center stretching, the next step is rolling the center lines of the metal sheet. Rolling is performed using the rolling units on the SBP press, consisting of upper and lower wheels running in opposite directions. Rolling stretches the metal and further shapes the panel, gradually bringing it closer to the desired contour. The rolling process primarily focuses on the center lines of the panel. Bending stamps can be joined together to create the optimal bending tool for both larger and smaller panels. Bending is often the last step in creating double curved panels and allows creation of the ideal shape. Using the intuitive user interface, the operator maneuvers the plate easily under the press to manage the forming process. Neyland's SBP shipbuilding presses provide the complete solution for the production of double-curved hull panels. These presses are suitable for bending, spot stretching, and rolling. The combination of these three applications makes the press the perfect solution for the efficient production of 2- and 3-dimensional shaped panels. Tool changes can be performed quickly and easily, allowing operators to process and shape complex panels in one operation. The SBP types range from 2,750 kilonewtons up to 15,000 kilonewtons. Each press can be equipped with specific tools for the following purposes. Rolling. A PWU rolling unit consists of an upper and lower wheel that run in opposite directions. Depending on the targeted shape, rolling is frequently the first step in the forming process and is used to stretch certain lines on the panel. Rolling is a highly effective way to form a complex shape. The only effect it has on the material is that metal is being strengthened. The surface remains smooth. Quality control. Throughout the production process, quality control measures are implemented to ensure the bulbous panel meets the required specifications. This includes checking dimensions, surface quality, and structural integrity. Any imperfections or deviations are identified and addressed to ensure the panel meets the necessary standards. The lines in the center of the bulbous bow are longer than the lines on the outside of the panel. For this, the bulbous panel is produced by giving center stretch first, and by rolling the center lines, the operator will soon get the basic shape for a bulbous panel. Getting the final shape is achieved by subsequent use the shorter bending tools. Stamping in specific situations, often related to small panels, stamping is the best way to create a shape. For this, Neyland's SBP press can be equipped with a toolset which includes a variety of top and bottom dies. Final shaping with shorter bending tools. Once the basic shape is obtained through center stretching and rolling, the final shaping is achieved by using shorter bending tools. These bending tools, which are specifically designed for shaping smaller sections of the panel, allow the operator to fine-tune the curves and contours of the bulbous panel. The metal sheet is carefully manipulated and pressed using the bending tools to achieve the desired final shape. The actual production time for the bulbous panel on the SBP press was 4 hours. It is important to note that the production time can vary depending on factors such as the size and complexity of the panel, operator expertise, and any additional steps or requirements specific to the project. The Amada hydraulic press brake is a sophisticated machine used in metal fabrication and bending processes. It utilizes hydraulic power to bend and shape metal sheets with high precision and accuracy. Let's explore how it works. The primary components of the Amada hydraulic press brake include a hydraulic system, a bending ram, a bed or table, and a back gauge system. The hydraulic system is responsible for generating and controlling the required force for bending the metal sheet. It consists of a hydraulic pump, cylinders, valves, and a control system. The process begins by positioning the metal sheet on the bed, which is equipped with a V-shaped groove or a tooling set. The back gauge system aligns the sheet to ensure accurate bending positions. The operator then sets the desired bending angle and length on the control panel. Once the parameters are set, the hydraulic pump delivers hydraulic fluid under high pressure to the hydraulic cylinders. These cylinders are connected to the bending ram, which moves downward to exert force on the metal sheet. The force applied by the ram causes the sheet to bend along the V-shaped groove or against the tooling set. The hydraulic system ensures a smooth and controlled movement of the ram, allowing for precise bending. The operator can adjust the force and speed of the ram based on the material type and thickness, ensuring optimal results. The back gauge system assists in maintaining accurate positioning and repeatability for multiple bends on the same sheet. Advanced Amada hydraulic press brake models incorporate CNC technology, enabling automated and programmable bending operations. The CNC control system provides increased productivity, versatility, and ease of use. It allows the operator to store and recall bending programs, making it suitable for complex and repetitive bending tasks. SCN Machinery, based in Taiwan, specializes in the manufacturing of high-quality hydraulic presses for the automotive industry. Their car body panel press, boasting an impressive 2,000-ton capacity, is specifically designed for stamping car panels through deep drawing techniques. Deep drawing is a metalworking process that involves transforming flat sheet metal into complex three-dimensional shapes. In the automotive industry, deep drawing presses play a crucial role in the production of car body panels, such as doors, fenders, hoods, and roofs. The SCN car body panel press utilizes hydraulic power to exert immense force on the sheet metal, ensuring precise and consistent deep drawing results. This advanced technology enables the production of car panels with high structural integrity, dimensional accuracy, and surface finish. At Macquarie Engineering Limited, the largest single-span press brake in operation is the 600-ton, 7 meters EHT TrueBend. This impressive piece of equipment is utilized for sheet metal fabrication, allowing for efficient and precise bending of large metal sheets. The key feature of the largest single-span press brake is its impressive tonnage capacity of 600 tons. This means that it can apply an immense amount of force to the metal sheet, allowing for bending even of thick and heavy materials. The 7-meter span refers to the length of the machine's bed, providing ample space for accommodating large metal sheets. To operate the press brake, the metal sheet is first loaded onto the machine's bed. The operator then sets the desired bending angle and position, as well as the appropriate tooling for the specific bending operation. Once the setup is complete, the machine's hydraulic system engages, applying the necessary force to bend the metal sheet. The press brake is equipped with lifting aids, which assist in handling and positioning the heavy metal sheets. This feature ensures that the bending process is not only efficient, but also safe for the operators. It's crucial in the construction of bridges and roads, as it provides a stable foundation that can support heavy loads and withstand various environmental factors. Piling involves driving or drilling deep structural elements, called piles, into the ground to transfer the load of the structure to deeper, more stable layers of soil or rock. This section shows the piling process of the project on Foxton Road in Birmingham. It involved Bachy Solatench being awarded a contract to install a 12.5 meter diameter, 14 meter deep cased secant piled (CSP) shaft. They were also responsible for designing and constructing a temporary jet grout plug at the base of the shaft. In the piling process, the piling rig drills a borehole into the ground using a rotating drilling tool. The tool may have a cutting or drilling bit, depending on the soil and rock conditions. The drilling continues until the required depth or the design specification for the pile is reached. Once the borehole is drilled, reinforcing steel bars, known as reinforcement cages, are inserted into the hole. These cages provide additional strength to the pile and help it withstand the structural load. The secant piles used in the project were 880 millimeters in diameter and 18.0 meters long, and they were installed using the CSP technique. This technique combines the verticality of rotary piling with the production rates of CFA, continuous flight auger. The piling process used in the project involved the installation of secant piles using the CSP, cased secant piled technique. Here is a more detailed explanation of the piling process. Secant piles. Secant piles are structural elements made of reinforced concrete that are installed next to each other to form a continuous wall. In this project, the secant piles had a diameter of 880 millimeters and a length of 18.0 meters. They were designed to interlock with each other to create a watertight and stable structure. Cased secant piled (CSP) technique. The CSP technique involves the use of a casing during the installation of the secant piles. The casing provides support and prevents the collapse of the surrounding soil during the drilling and concreting process. It ensures the integrity of the piles and allows for the construction of deep and vertical piles. One of the key challenges of the project was the high water table and the permeable soil conditions. To address this, a temporary jet grout plug was constructed at the base of the shaft. This plug acted as a groundwater cutoff, preventing water ingress during the excavation of the shaft and the construction of the permanent base slab. The jet grout plug was built up using primary, intermediate, and secondary columns of different diameters. The overlapping of these columns was verified through measurements using the in-house Silejet geophysics testing system. The ground conditions at the site consisted of approximately 2.5 meters of made ground, followed by loose to medium dense silty fine and medium sand. The proximity of residential housing and the access road required careful consideration during the piling operations. A Clem 700 4:1E drilling rig, equipped with NPAJet, the in-house computer control and recording equipment for jet grouting, was used for constructing the jet grout columns. The use of this electrically powered rig helped minimize environmental impact through reduced noise and emissions. The quality and diameter of the jet grouting were checked using the SileJet system, which employed soil resistivity surveys. Trial columns were constructed outside the shaft perimeter to ensure proper construction technique and quality. The construction of the plug involved starting from ground level and installing vent holes to allow air pressure to dissipate as the plug was closed. Once the shaft was successfully excavated, permeability testing was carried out. Falling head tests were conducted in situ to determine the permeability of the jet grouted material. Additional testing on core samples confirmed that the base plug had a permeability in the range of 1x10 to 9 meters per second, which is typically associated with cutoff barriers. Let's explore some of the types of drills commonly in big construction projects. Cased auger drill. The cased auger drill is one of the primary drilling tools used by Malcolm Drilling. This type of drill consists of a hollow steel auger encased in a temporary steel casing. It is particularly useful in soft to stiff clay, silt, and sand formations. The auger's rotation helps in breaking the soil or rock formation, which is then removed using the auger flights. The temporary casing provides stability to the hole during the drilling process. Continuous Flight Auger CFA drill. The CFA drill is widely employed by Malcolm Drilling for constructing drilled shafts in various soil conditions. It involves a hollow stem auger with a continuous flight, allowing for the extraction of soil or rock cuttings by reverse circulation of drilling fluid. This method ensures minimal soil disturbance, making it suitable for urban environments where ground settlement needs to be controlled. Kelly bar drill. The Kelly bar drill is a versatile drilling rig equipped with a telescopic or interlocking Kelly bar that transmits torque and downward force to the drilling tool. This type of drill is ideal for drilling large diameter, deep shafts in dense soil and rock formations. The Kelly bar drills are used for constructing deep foundations, such as drilled shafts and secant piles. This construction project has applied the augered cast-in-place pile method. This method involves using a large diameter steel pipe, known as an auger, to excavate the soil or rock and create a hole for the pile. A large diameter steel pipe, known as an auger or casing, is driven or drilled into the ground using a crane or drilling rig. The auger is inserted vertically into the ground to the desired depth. Once the auger is in place, an excavator with a bucket is used to scoop out the soil or rock from inside the auger. The bucket is lowered into the auger and then lifted, removing the excavated material. The fabrication of a circular cage is an important step in the reinforcement placement process for augered cast-in-place piles. This circular cage, consisting of steel bars, provides structural integrity and enhances the load-bearing capacity of the pile. Here's a detailed description of the fabrication process. Steel bar selection. High-strength steel bars, typically with a circular cross-section, are selected based on the design requirements and load capacity specifications of the pile. The bars should have the necessary strength and ductility to withstand the forces imposed on the pile. Bending the steel bars. The selected steel bars are bent into the desired circular shape to form the main reinforcement cage. This is done using specialized bending equipment or by skilled workers who carefully shape the bars according to the specified diameter and configuration. Interconnection of bars. The bent steel bars are then interconnected by using transverse ties or spirals. These ties or spirals maintain the spacing and alignment of the bars, ensuring the structural integrity of the cage. The ties or spirals are attached at regular intervals along the circumference of the cage. Welding, if applicable. In some cases, welding may be used to secure the connections between the steel bars and ties or spirals. Welding ensures a strong bond between the components of the cage, enhancing its stability and load-bearing capacity. Welding should be performed by qualified welders following the appropriate standards and procedures. Checking dimensions and quality. Once the circular cage is fabricated, it is important to check its dimensions and quality. Measurements are taken to verify the diameter, spacing, and alignment of the steel bars. Additionally, visual inspections and quality control checks are conducted to ensure that the fabrication meets the required standards and specifications. Circular cage installation. After fabrication and quality checks, the circular cage is transported to the construction site and carefully lowered into the pile excavation. During the circular cage installation process, the goal is to carefully position the cage within the pile hole to ensure optimal load distribution and alignment. The circular cage is lowered into the pile hole using a crane. Care is taken to position the cage centrally within the hole, aligning it with the desired pile location. This ensures that the load-bearing capacity of the pile is evenly distributed and that the cage is properly aligned with any adjacent piles or structural elements. Throughout the installation, the verticality and alignment of the cage are monitored. Laser-guided equipment or other measuring devices may be used to ensure that the cage remains plumb and aligned with the design specifications. Adjustments can be made as needed to maintain the desired position and alignment. Splicing of cage segments, if applicable. In cases where the length of the circular cage exceeds the available single-piece length, splicing is performed to connect multiple segments together. This is typically achieved by overlapping the longitudinal bars of adjacent cage segments and securely tying them using appropriate steel wires or mechanical connectors. The splicing ensures continuity and strength throughout the length of the cage. Concrete pouring. Once the circular cage is correctly positioned and any necessary splicing is completed, the concrete pouring process begins. Tremie pipes are commonly used for concrete placement in deep foundation piles. The tremie pipe, with its bottom end submerged in the concrete, ensures that the concrete is poured from the bottom up, displacing any water or slurry present in the pile hole. Tremie pipe withdrawal. As the concrete is poured, the tremie pipe is gradually withdrawn from the hole to maintain a proper flow of concrete and prevent segregation. The rate of withdrawal is carefully controlled to ensure a continuous and uniform filling of the pile hole with concrete. This method helps to minimize the risk of voids or honeycombing within the pile. Concrete level control. During the concrete pouring process, the level of the concrete is continuously monitored and controlled to ensure that it reaches the desired elevation. Proper compaction techniques, such as using vibrators, may be employed to eliminate air pockets and achieve full compaction of the concrete around the reinforcement cage. Curing. After the concrete pouring is completed, the pile is left undisturbed to cure and gain strength. Curing is essential to ensure the development of the desired concrete properties, such as strength and durability. The curing process typically involves protecting the pile from excessive moisture loss and maintaining appropriate temperature conditions. Cutting the concrete head. After the concrete has cured and hardened, the protruding concrete head of the pile is cut using a cutter or saw. This step is necessary to create a clean and even surface for further operations and to expose the rebar ends. Drilling through the concrete body. Once the concrete head is cut, the next step involves drilling holes through the remaining concrete body of the pile. These holes are typically created around the perimeter of the pile using a drill equipped with a suitable drill bit. The spacing and depth of the holes may vary depending on the size and design of the pile. Attaching a cable for extraction. A cable is connected to the exposed rebar ends or inserted through the drilled holes and secured to the reinforcement within the pile. This cable is then connected to a crane or other heavy lifting equipment, which applies an upward force to extract the pile from the ground. Pile extraction. With the cable securely attached, the crane begins to lift the pile vertically, exerting a pulling force. As the pile is lifted, the soil or other supporting materials around it may be loosened or disturbed. The extraction process continues until the pile is completely removed from the ground. The construction process of the viaduct over the Contreras Reservoir, located in the ASV, Lave Madrid, Levante section from Contreras Reservoir to Villargordo del Cabriel, was a remarkable engineering feat. The entire section, spanning 6.5 kilometers, included 3 viaducts and 3 tunnels. The construction work was completed after more than 3 years of construction. Black Slope Viaduct is located after the Hoya de la Roda tunnel and spans a deep ravine. The construction process of the Black Slope Viaduct involved the initial construction of the foundations and footings of the piers. The piers were built using climbing formwork in sections of 5 meters. Once the formwork was in place, passive and active reinforcement were installed. The viaduct's deck was constructed using a portable formwork system composed of metal towers and 12-meter-long profiles. After the reinforcement was placed, the concrete was poured in 2 phases. Once the concrete had hardened, the formwork was removed, and the process was repeated for the next span. The Isthmus Viaduct, with a length of 830 meters, was designed to traverse a rocky ridge and connect the different sections of the Madrid-Levante high-speed line. The construction of the viaduct began with the execution of the foundation piles using a self-climbing formwork system. This involved opening the formwork and lifting it into position, followed by the placement of passive reinforcement and the pouring of concrete. The piles, characterized by their hollow section, were constructed to a height of up to 70 meters above the foundation. Once the piles were completed, the construction of the deck commenced. A self-launching formwork system was utilized, consisting of a large metal structure with the ability to advance longitudinally. The process involved the placement of passive reinforcement and active steel cables, partial stressing of the cables, and the pouring of concrete in 2 phases. Pre-slabs were then used as permanent formwork, and the second phase of concrete pouring took place. This process was repeated for each span of the viaduct, with a maximum span length of 66 meters. The construction of one complete span was achieved approximately every 2 weeks, showcasing the efficiency and expertise of the construction team. Throughout the construction process, stringent quality control measures were implemented to ensure the structural integrity and safety of the viaduct. Regular inspections were conducted to verify the correct placement of reinforcement, the quality of the concrete, and the overall alignment and geometry of the viaduct. The completion of the Isthmus Viaduct was a significant milestone in the construction of the Madrid-Levante high-speed line. providing a vital link in the transportation network and showcasing the engineering prowess and innovation involved in overcoming challenging geographical obstacles. Spanning a length of 587 meters, the Contreras Viaduct was designed to cross the Contreras Reservoir, making it the largest arch bridge on a concrete structure in Spain and Europe. The construction process of the Contreras Viaduct began with the execution of the foundation and piers. Temporary piers were erected using self-climbing formwork, which allowed for the construction of the arch in a cantilevered manner. The formwork system provided support during the construction process. Once the temporary piers were completed, work on the arch began. To construct the arch, a combination of advanced construction methods was employed. The construction team used a sophisticated launching gantry system, which facilitated the construction of the arch in a segmental manner. The launching gantry was a large-scale metal structure that moved along the arch's alignment, allowing for the placement of formwork and the pouring of concrete. The construction of the arch proceeded in segments known as develas. Each devela measured 3 meters in length and was poured in 2 phases. The first phase involved placing passive reinforcement and pouring concrete to form the lower part of the devela. Once the concrete had cured, the second phase commenced, which consisted of pouring the upper part of the devela. This method ensured the stability and integrity of the arch during construction. As the construction of the arch progressed, temporary support systems, including suspended cables and metal pylons, were installed to provide additional stability. These systems helped distribute the loads and stresses during the construction process. Once the arch was completed and achieved continuity, the temporary support systems were removed. The arch's load was transferred to the permanent piers, which were constructed using the same techniques as the temporary piers. The removal of the temporary support systems allowed for the finalization of the viaduct's construction. After the completion of the arch and piers, the construction of the viaduct's deck began. A cantilever construction method was employed, utilizing a self-launching formwork system. The formwork, supported by a large metal structure, allowed for the gradual advancement of the deck construction. This process involved the placement of passive reinforcement and active steel cables, partial stressing of the cables, and pouring of concrete in 2 phases. Pre-slabs were used as permanent formwork, ensuring the overall stability and strength of the deck. Throughout the construction process, rigorous quality control measures were implemented to ensure the viaduct's structural integrity. Inspections and testing were conducted regularly to verify the proper placement of reinforcement, the quality of concrete, and the alignment and geometry of the viaduct. The construction process of the viaduct Highway A27 in its section between Valls and Mont Blanc was carried out by Tecoxam, and here is an overview of the construction process. The project was divided into 2 phases, with each phase focusing on one roadway of the viaduct. The construction began by executing the foundation works, which involved the construction of the pile supports for the viaduct. The piles, reaching a height of over 27 meters, were constructed using climbing formwork techniques. The structures are hyperstatic of post-tension concrete with a light gull section with variable edge, varying the edge of 1.50 meters in stirrups, pile 1 and 4 and center of span 3 to 3.00 meters in piles 2 and 3. The highest pile it is pile 3 on both roads, exceeding 27 meters in height. Once the foundation works were completed, the construction progressed to the erection of the superstructure. The viaduct's superstructure consisted of post-tensioned concrete elements with a variable edge gull shape. The construction team utilized a cantilever construction method, using formwork systems to shape and pour the concrete elements. The construction of each roadway proceeded in separate stages. In the first phase, 2 spans were constructed along with the 5th span, covering a length of 80 meters. The second phase focused on the remaining 3 spans, extending the roadway by 100 meters. This section shows the girder launching process of the viaduct over the Ferrera River in Gunton, Lugo, Spain. This hyperstatic viaduct comprises 5 bays with lengths of 456060-60 to 45 meters and features a double sidewalk towering at a maximum height of 60 meters. The transportation of the massive bridge girders to the construction site is entrusted to Technotruck, a renowned company in the field. Upon arrival at the construction site, the truck from Technotruck carefully maneuvers in reverse, approaching the girder launching system. This system serves as the crucial apparatus for transferring and installing the girders onto the piers. Girder launching, also known as bridge launching or bridge construction using the incremental launching method, is a technique employed to build bridges without the need for traditional scaffolding or temporary support structures. It involves constructing the bridge incrementally, launching each section, girder, from one end of the bridge to the other. The process begins with the construction of temporary piers or support structures on one side of the bridge. These structures act as launching pads for the girders. The girders are typically precast and assembled on-site or nearby. Once the first girder is ready, it is moved onto the launching pad using hydraulic jacks or launching nose systems. These systems provide the necessary force to push the girder forward. As the girder moves, it slides along the previously placed girder and is supported by rollers or sliding bearings. The launching process is repeated for each subsequent girder, with the previous girder acting as the support for the next one. This incremental method allows the bridge to be constructed gradually, reducing the need for extensive scaffolding. The construction of the Baling River Bridge, also known as Balinga Bridge, took place in Guanling County, Guizhou Province, China. The project aimed to create a vital transportation link as part of the G60 Shanghai Kunming Expressway between Kunming and Guiyang. The bridge spans the Baling River Valley. The bridge is part of the G60 Shanghai Kunming Expressway between Kunming and Guiyang and reduced the travel time across the river valley from 1 hour to 4 minutes. The suspension span is 1,088 meters, 3,570 feet long, and the bridge has a total length of 2,237 meters, 7,339 feet. It is also one of the world's highest bridges with 370 meters, 1,210 feet, of clearance above the river. The construction process began with extensive planning and design studies to determine the optimal structure for the bridge. Excavation work was carried out to prepare the ground for stable foundations, and piers and towers were erected to provide support. The main feature of the bridge is its suspension span, which measures 1,088 meters, 3,570 feet in length. High-strength steel cables were carefully installed, connecting the towers and providing the necessary stability. These cables were tensioned to ensure the bridge's load-bearing capacity. Once the cables were in place, the construction of the bridge deck commenced. Steel trusses or girders were assembled section by section and attached to the suspension cables. Concrete reinforcement and asphalt surfacing were applied to create a smooth road surface for vehicles. Quality control measures were implemented throughout the construction process to ensure the bridge's structural integrity and safety. Additional finishing touches, such as guardrails, lighting, and road markings, were added to complete the project. The Bailing River Bridge, with its impressive clearance of 370 meters, 1,210 feet above the river, opened to public traffic on December 23, 2009. Its construction significantly reduced travel time, providing a vital transportation link between Kunming and Guiyang. Sheet Piling UK Limited was tasked with constructing 2 circular cofferdams at the outer harbour breakwaters, which formed the entrance to Great Yarmouth Harbour. The project had specific requirements, including completing the cofferdam installation works in 3 months and minimizing disruption to normal harbour activities and ship movements. Sheet Piling UK Limited decided to utilize a construction method that involved pre-assembling the sheet pile cofferdams on adjacent quaysites before lifting, floating, and positioning them using a large sheer leg crane barge. To begin the construction process, a robust temporary work support frame was fabricated and assembled on the quayside. The interlocking straight web sheet piles were carefully placed around the frame and secured at the upper level. Pile creep was closely monitored to ensure the closure of the circle without inducing strain. A jacket piling barge was mobilized and positioned at the designated installation location. The Smithtuck Lift 7 sheer leg barge was brought in for heavy-duty lifting. Lifting straps were connected to lifting points on the temporary work assembly. The fabricated cofferdam, weighing approximately 400 tons, was then lifted from the quayside and precisely floated into position using GPS positioning techniques. Once the structure was accurately lowered onto the seabed, 860 millimeters diameter tubular piles were vibrated to a depth of 5 meters to firmly anchor the cofferdam. The straight web sheet piles were sequentially driven to the required design level using a crane-suspended vibratory hammer. Hydraulic pumps were utilized to hydraulically place cell-fill materials from a land-based stockpile. Thanks to this innovative construction method, both cofferdams were accurately installed at the harbor entrance within a 1-week period, with no disruption to normal harbor operations. This construction approach, using cellular sheet pile cofferdams in tidal waters, was believed to be the first of its kind in the UK. The entire subcontract works were successfully completed by the contract deadline. The Hong Kong-Zhuhai Macau Bridge, also known as the HZMB, is an impressive infrastructure project that spans across the Lingding Channel, connecting Hong Kong, Zhuhai, and Macau. Notably, it holds the distinction of being the world's longest sea bridge, measuring approximately 55 kilometers in length. This remarkable sea-based construction incorporates 2 artificial islands, which serve as connectors for sections of the bridge, and features a remarkable 6.7-kilometer undersea tunnel. The components of the bridge were prefabricated on production lines before being transported and assembled at sea, showcasing the intricate planning and engineering involved in its creation. An incredible feat of construction, 33 tunnel elements were precast over a period of 53 months. These tunnel elements were then installed and seamlessly connected beneath the sea, demonstrating the precision and accuracy required to achieve such a remarkable project. The margin of error in the construction process was an astonishingly small 1.5 centimeters, emphasizing the meticulousness of the engineering team. The construction of the Hong Kong-Zhuhai Macau Bridge commenced on December 15, 2009, and after years of dedicated effort, the bridge was officially opened to traffic at 9 a.m. on a Wednesday. The Octokong hammer, manufactured by American Pile Driving Equipment Inc., APE, is recognized as the largest vibratory driver extractor in the world. In April 2011, the final assembly of the Octokong was completed, marking a significant milestone in its production. APE's team conducted rigorous testing of the hammer on a full-size test pile to ensure its reliability and performance. The Octokong was manufactured in the United States and then transported to China, where it was assembled for the construction of the Hong Kong-Zhuhai Macau Bridge. The specifications of the Octokong hammer are impressive. The pile it operates on has a diameter of 22 meters, 72 feet, and a length of 40 meters, 131 feet. The hammer itself weighs a staggering 450 metric tons, 500 US tons, with an eccentric moment of 1840 kilogram m, 160,000 N lbs, and a driver force of 40,000 kilonewtons, 4,450 US tons. The Octokong possesses immense power. It is driven by a 7,158 kilowatts, 9,600 HP motor, further highlighting its capability. The Bauer Group, specifically its subsidiary Bauer Hong Kong Limited, undertook the construction of offshore board piles with rock sockets. The project was carried out at the Hua 4 site office, located in Ta Kau Wan, Lantau Island, New Territories, Hong Kong. The construction process involved the mobilization of 4 BG-40 piling rigs, along with their accessories, to the site. These rigs are specialized equipment used for drilling deep foundation piles. The offshore bored piles with rock sockets were designed to provide a strong foundation for the bridge in the challenging marine environment. The construction work primarily focused on the Hong Kong Link Road, which consisted of a 9.4-kilometer viaduct with a dual 3-lane carriageway connecting the Hong Kong International Airport to the HKSAR boundary. In total, 12,600 tons of steel cages were installed as reinforcement within the board piles. These steel cages help to enhance the structural integrity of the piles and provide stability. Additionally, a significant amount of concrete, totaling 63,900 cubic meters, was placed to fill the board piles and create a solid foundation. The construction progress was impressive, with 3 to 4 piles being installed each week. This efficient pace allowed for the timely completion of the foundation works. The construction of an artificial island at the northeastern waters of the airport island for the project was a significant engineering endeavor that brought about several benefits for travelers and the environment. The creation of the artificial island provided immense convenience to travelers, offering a centralized location for processing cars, coaches, and goods vehicles traveling between Hong Kong and Zhuhai, Macau. Situated next to the Hong Kong International Airport, the HKBCF offered seamless connectivity to nearby highways and the airport, facilitating efficient transportation and enhancing overall accessibility. The road-immersed tube tunnel is a critical component of the bridge project, providing a seamless link between the artificial islands that support the bridge's main structure. With a total length of approximately 6.7 kilometers, 4.2 miles, this tunnel surpasses all previous records in terms of size and complexity. The construction process involved several remarkable engineering feats. First, large sections of precast concrete tunnel elements were fabricated and floated into position. These elements, known as tunnel sections, were then carefully immersed and placed onto prepared seabed trenches, creating a continuous tunnel structure. The connection between each section was precisely sealed to ensure water tightness and structural integrity. Due to the challenging underwater conditions and the scale of the project, extensive construction techniques were employed. Specialized marine vessels, cranes, and other heavy machinery were utilized to maneuver the massive tunnel sections into position, while divers and remotely operated vehicles were deployed for underwater inspections and maintenance. The construction process of the Wudongda hydropower station in China involved a series of remarkable engineering endeavors. Situated on the border of Sichuan and Yunnan provinces, the station was designed to have a total installed capacity of 10.2 million kilowatts, providing an average annual generating capacity of 38.91 billion kilowatts. One striking feature of the Wudongda hydropower station is its unique design, resembling an eggshell nestled in the V-shaped valley of the Jinsha River. The double-curved arch dam stands at a maximum height of 270 meters, while maintaining an average thickness of only 40 meters. This makes it the thinnest 300-meter arch dam in the world. The eggshell shape was carefully chosen to strike a balance between security and economic factors, optimizing the dam's performance in its specific location. Despite its slender profile, the dam effectively blocks the river and creates a reservoir capable of storing approximately 7.4 billion cubic meters of water. Notably, the construction of the dam marked a global first, as it was entirely built using low-heat cement. This innovative choice of materials ensures greater stability and significantly reduces temperature stress on the dam, addressing a common challenge in dam construction worldwide. Given the narrow space between the mountains flanking the top of the dam, many structures associated with the Wudongda hydropower station were built within the mountains or underground. The primary workshop, which houses the generator units, is located on both sides of the dam within the mountains. Each side accommodates 6 hydroelectric generating units, with a capacity of 850,000 kilowatts per unit. The main workshop spans an impressive length, equivalent to 3 standard football fields, and reaches a height of 89.8 meters, making it the tallest underground power plant in the world, equivalent to a 30-story building. The construction of the Wudongda hydropower station showcases China's commitment to pushing the boundaries of engineering innovation and sustainable energy development. With its remarkable design and impressive capacity, this hydropower station represents a significant milestone in China's pursuit of clean and renewable energy sources.